Okay, chapter 17 is additional aspects of aqueous equilibrium. There are basically three parts to this chapter. There are buffers, then we have titrations, and then we're going to look at KSPs or solubility products. So we're going to start off here with buffers, and that starts out with common ion, the common ion effect. So here we looked at last chapter dealing with Le Chatelier's principle with common ions. If I add an ion that's already in a solution, which way is it going to shift? So if we have something like HC2H3O2, that's going to break apart into H plus and C2H3O2 minus. And if I would add like NaC2H3O2, so sodium acetate, the sodium again is not really doing anything. It's our spectator ion. So in essence, I'm just adding some more acetate ion, which would mean that I'm adding more of this. Well, if I add more of that, that means it's going to shift to the left to undo that. And that is really just the common ion effect there. You're going to use more of your H plus up. So if I use more H plus there, I'm going to also then make more of my acetic acid. So it's the same thing as we were dealing before with our ice tables. There just might be kind of two initial numbers versus one. So let's look at an example. Okay, if I have the pH of a solution that's made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate, and I'm going to use enough water to make a 1 liter solution. So again, we're looking at acetic acid, and you can kind of look at it from either viewpoint, whether it's the HC2H3O2 or whether it's the acetate ion. It's going to depend on whether you use a Ka or Kb, and I would tend to go with using the Ka because it's usually what you're given. So we're going to look at it from the acid's point of view. So eventually I am going to need a Ka value, which again you can look up, and that's going to be 1.8 times 10 to the negative fifth. Now if we do kind of our ice tables here, I have my initial. In this case I have two things that I'm adding together. So I have 0.3 moles of that acetate ion, which means I have a 0.3 molar solution because it's 1 liter. I don't have any of the H plus to begin with, but I am adding that same amount of sodium acetate, which means I have a 0.3 molar solution of the acetate ion. So here I'm still shifting to the right because I don't have any H plus to start with. And I'm going to use my Ka and plug all my numbers in. Products over reactants, so x times 0.3 plus x over 0.3 minus x. And again, we're looking at these small Ka's, so I can just disregard these plus x's. And I'm really going to end up with then my 0.3's canceling. So really, my x is 1.8 times 10 to the negative fifth. And that is my H plus concentration. So that means that I can just take the negative log of 1.8 times 10 to the negative fifth. Just going to do my pH, which is going to be 4.74. Okay, 17.2 is on buffer solutions. And a buffer is just a solution that resists a drastic change in pH when you add either more acid or more base to it. So its pH is not going to change much if I add either acid or base to it. Good examples are your blood. That's a good buffer. If I add acid or base to it, your pH in your blood shouldn't change very much. And then you also have seawater. That is a very good buffer as well. Okay, in order to make a buffer, you need to have a weak acid and its conjugate base, because you need the base to neutralize the acid, and in case you add acid to it, you need the acid to neutralize any added base. So it can't be a strong acid because you won't have any equilibrium. That's why it has to be a weak one. Because remember, a strong acid or a strong base are going to totally dissociate. So you can't have anything that's going to be strong, which is why you got to have a weak one. So I've got to have something HX, any weak acid, and its same then conjugate base. Okay, I need the acid to react with the base that I add, and the base to react with the acid that I might add. So here's how a buffer actually works. Okay, so if I have this in terms of the weak acid, okay, if I add acid to it, so that means that I'm going to add H plus. Well, if I add H plus, the H plus is going to want to react to form HX. So it's kind of like we're going to shift over there to the right. So you add H plus, it's going to react with the X minus, and it's going to make H plus X minus is going to yield my HX. Okay, so you're adding an acid, but I am forming an acid. Okay, and you're also then going to use up some of the base as well in the reaction to get it to make more of the acid. So whatever you're adding, you are in essence undoing. Okay, now if you add a base to this buffer, okay, my OH minus is going to react with the acid. It's a base, so it reacts with the acid, HX, and it's going to form X minus. So if you add a base, I'm forming a base. You're undoing what you just did. Of course, you're going to have water there as well. Okay, but also, again, then we're going to use up a little bit of acid in the reaction as well. So let's look at the picture that you have there to the right of all of this. Okay, if I have my buffer in the middle, equal concentrations of the weak acid and its conjugate base. Okay, if I add some acid to it, the H plus is going to want to react with the base to form an acid. So I added an acid, I'm forming an acid. But notice how the F minus has a little bit smaller concentration than it did before because you're using up some of it to react with the acid that I added. If you go the other direction, I add OH minus, the OH minus is going to react with the acid that I have, which is why you lose some right here. Okay? But I'm adding a base, I am forming a base, F minus. So notice how as much as one lost, the other gained. Okay, you have to undo what you just did. So if we're going to calculate the pH of a buffer, there's kind of a long route and a short route. You can use the common ion effect and you can figure out with your ice tables and with the equilibrium. It's a little bit easier if you actually use an equation, and this equation is given to you on your green sheet, and we're kind of going to go through how they got this equation. So remember, Ka is going to be H plus times X minus all over HX. Products over reactants is Ka, so I'm looking at it in terms of HX falling apart into X minus and H plus. And if I rearrange, if I solve for my H plus because I want a pH, so I'm going to have my H plus is equal to the Ka times HX concentration all over my X minus concentration. To get this to go from an H plus to a pH, you take the negative log. So I'm going to take the negative log of the H plus concentration. Only time you deal with logs, if you divide, you're actually subtracting. So I have the negative log of my Ka minus the log of your HX over my X minus. And if I get rid of all those lovely logs and put p's instead, I can have my pH is equal to the pKa minus, or plus, sorry, the log of X minus over HX. Okay, it's in equilibrium, but your Ka is so small that it's actually really your initial. So you're just kind of simplifying your logs here, and you end up kind of flipping it and making it a positive. So this is what we call the Henderson-Hasselbalch equation. It is on your green sheet, and it is the easiest way to find the pH for a buffer. Now, I think on your green sheet it might say concentration of your base over concentration of your acid, but either way. Okay, so let's try the next one, and we're going to do this one two ways. Okay, one is the pH of a buffer that has a 0.21 molar solution in lactic acid and a 0.10 molar of sodium lactate, and the lactic acid Ka is given there. So I could go the route we were doing earlier with the common ion effect and do HC3H5O3 and how that falls apart. Because again, this sodium really doesn't do anything, so I'm looking at this minus. Okay. I have a 0.12 molar solution of the lactic acid. I don't have any there, and I've got 0.1 here. That way I'm shifting to the right. I've got my Ka, which is 1.4 times 10 to the negative fourth. Products over reactants. Remember, we can get rid of the plus x. I'm just going to do that right now. Get rid of the minus x. Cross multiply and divide. And I'm going to get an x value of 1.7 times 10 to the negative fourth. That's my H plus concentration because it is what I'm looking for right there on the right side, the negative log of that, and I'm going to get 3.77. So that's using the common ion effect to figure out this problem. We can also use the Henderson-Hasselbalch equation to figure this out because it's the same thing, just simplified. So I've got my pH When I figure that out, it's going to be the negative log of my Ka, which is 1.4 times 10 to the negative fourth, plus the log of the 0.10 over the 0.12, and I get a pH of 3.77. So it's the same thing. Here you just got to know which one's the base and which one's the acid. Go ahead and try the next one. Okay, we should get 0.36 moles. This one's a little bit backwards in the fact that they gave you the pH, so that means I can get the POH. Get the POH, I can get the OH minus concentration, which means I can get that and use that in my equation here. You can plug it in then with your KB and solve for X, which in this case is my NH4 plus concentration, or NH4Cl. So I get that molarity, molarity times volume equals moles. Remember, molarity is moles per liter. Okay, the capacity for a buffer. Okay, the amount of acid or base that can be neutralized by the buffer without the pH going up or down. They're not forever. So the buffer capacity depends on the concentration of your components in the buffer. The greater the concentration of your weak acid and conjugate base, the greater the capacity because you have more ions there to absorb. So they do kind of have a limit. At some point in time, the buffer will stop working because all the ions that are possibly there to be able to use up whatever you're adding are already themselves used up. Okay, so now we got a pH range. Okay, pH range over which your buffer is effective. They are most effective when the conjugate base and the weak acid concentration are the same. And those are equal when your pH equals your pKa. Remember, we did a whole lab on that. So they're equal when that occurs. So your pH range is within 1 pH unit of the pKa of the buffer. Okay, and then that next part there, the addition of the strong acids or bases to buffers, we actually already kind of talked about. So I'm just going to summarize it again really quick so we make sure what we're doing. And then we're going to look at some problems. So again, you've got one of two options, whether you're adding a strong acid or a strong base. You add a base, it's going to neutralize it with an acid to make more base. You add an acid, it's going to neutralize it with a base to make more acid. So let's go ahead and look at the practice problem here. Okay, buffer is made by adding 0.3 moles of HC2H3O2 and 0.3 moles of the sodium acetate. Notice how these two are equal. Since those two are equal, that means your pH is equal to your pKa. Okay, and it's added to enough water to make 1 liter. The pH of my buffer is 4.74. I want to calculate the pH of the solution after 0.2 moles of NaOH have been added. So the first thing we're going to do is determine how much OH reacts with the buffer and what's left. And then we're going to use our Henderson-Hasselbalch to determine the actual pH for the buffer. So if I add OH minus to it, the OH minus is going to react with the acid, which is the HC2H3O2. All right. The base is going to gain the hydrogen, so I'm going to make water. The acid is going to lose the hydrogen, so I have the leftover conjugate base. Okay. I originally had the buffer being 0.3 molar, and then 0.3 molar. So this is before you add. You're going to add 0.02 moles of the NaOH. So I have 0.02 moles here, which means I'm going to use up 0.02 moles. Since it's 1-to-1, so I'm going to have 0.280 moles left over. The water I don't care about because it's a liquid. I'm going to then shift to have 0.02 moles of the base being made since it's 1-to-1 again. So here I'm adding, so I've got 0.32 moles. So this is after you add. I don't have any OH minus left, which would make sense because you're neutralizing all of it. So I'm going to get rid of all of that. So I have none of that left. I don't care about my water, and this is how much acid I have left and how much base I have left. So the pH is what I'm looking for. I need the pKa. Well, they don't tell me the Ka, but they do tell me that those two things are the same in the buffer, which means my pH is equal to my pKa. So I have 4.74 plus the log of the base over the acid, and the base is the 0.32, and the acid is the 0.280. Plug in your calculator and you get 4.80. Notice how it did not change very much, and it shouldn't because it's a buffer.